It's my pleasure to introduce our moderator for today, and that is Mark Weiss of Mark Weiss Consulting. Mark, I'll turn it over to you.
Thank you. Good morning. Well, good afternoon. Hello. And today's webinar is actually entitled, Is GPS More Vulnerable Than Ever? And it is valuable, and I appreciate the introduction. For those of you who are unfamiliar with ATIS, it is a technology and solutions development organization with nearly 200 companies actively participating in its industry forums. ATIS brings together the top global ICT companies to advance the industry's most pressing business priorities. During today's discussion, I encourage you to submit any questions that you may have online. We will hold the questions until the end of the presentations, and we'll try to get to as many of your questions as possible. In addition, slides will be distributed via email to all registered participants, as well as a recording. Now I would like to introduce today's topic and our speakers. While GPS vulnerabilities have a potentially devastating impact on a broad range of sectors, major inroads are being made to address them. This webinar provides insight by bringing together government experts, network operators, as well as manufacturers of receiving devices and timing technologies. Our presenters today are Richard Lindsey, a data architect engineer for Windstream Communications, Richard Funderburk, timing systems architect for Trimble, and Sarah Mahmood with Science and Technology Directorate of the Department of Homeland Security. Richard, Sarah, and Richard, thank you for joining us today. So I will begin by giving a brief overview of the topics. My first slide should now be on the screen, and of course, the title is GPS More Vulnerable Than Ever. So I'm going to start with just a picture of how time from GNSS or GPS works. GNSS, of course, is a generalization of any global navigation satellite system, though we are focusing on GPS particularly. And this will give an overview of both the intentional and unintentional error sources. GPS works by transmitting time and satellite position. Satellites get these as predictions in upload. So the fundamental information you get from GPS is a prediction. And the first part of that is the satellite gets time and ephemeris or position from the ground and then transmits that typically about once per day. It gets an upload. And so there can be issues there. And then the signal travels from the satellite to the Earth, and in the process, it's delayed as it goes through the ionosphere and troposphere. In particular, the ionosphere is vulnerable to solar weather, and the troposphere can add in damping due to moisture and rain that can make the signal weaker. But most of the issues that we face day to day are issues at the receiver, things improperly set up in terms of coordinates, multipath interference around the antenna. Jamming and spoofing are probably the only ones that can come as intentional error sources. And then there are other issues that can happen. Delays in the cables have to be accounted for, delays through the receiver, and the receiver software has to function properly. So that's a quick list of sources of errors in GPS. Probably the most common source of problems is the way the antenna has been installed. This is a picture of antennas that have been put in places that cause a lot of multipath and potential interference. There can be signals that are transmitted from neighboring antennas that interfere. and bouncing off signals next to large buildings, antennas next to large buildings can cause problems. So this is a picture of some of the issues. For intentional problems, there are illegal jammers that are advertised on the web, in particular this so-called personal privacy device. We see evidence that a fair number of these are in use. People buy them to keep from being tracked in their vehicles or trucks or whatever they're using. And there's an array of jammers that can be bought and used for various purposes. There are also, we have evidence of military jammers being used against countries. That's not a particular issue in the United States at this point. The other issue that can happen is spoofing. And in spoofing, a counterfeit GPS signal is transmitted, and there's the correct one in this picture that's blue, and this dotted red one is moving up to match the correct one, and then it matches it and becomes more strong and then can pull off the lock of the receiver. So that gives a couple of brief overviews on what the issues are with GPS and how it's vulnerable to various sources of problems. I'm now going to hand the talk over to Richard Lindsey, who will continue. Thanks, Richard.
Thank you, Mark, and thank you for getting this information webcast together today. It's definitely needed in the industry to bring information. So as Mark pointed out, as a carrier, we have looked at over the past 2 to 3 years and collected statistical data on the different spoofing, jamming, and other impacts to GPS because of the critical nature of GPS into the carrier networks, which we'll go through in a little bit. So we've identified and classified basically 3 types of impact. The first is an intentional sabotage, as Mark pointed out, spoofing or jamming type condition, where we actually have an individual or organization attempting to change the time of day stamps to alter the analyzation of data or impact time frames of data or video. That only accounts for about 3% of what we actually saw statistically over the past 2.5 to 3 years. The largest of the impacts to GPS services that we've actually recorded is under the collateral sabotage. The reason we use that terminology in the industry is because these are non-intentional impacts to GPS. The biggest impacts that we have identified is from truck drivers. When GPS were added to trucks to allow their organizations to be able to say new regulations where the truck driver has to stop at the nearest truck stop, park his vehicle, and not allowed to take that truck all the way to his home, which might be 85 or 90 miles to his home from the nearest truck stop. Well, that's an additional 160, 170 miles on the truck, so they tried to limit that. Well, the truck drivers, to get around it, started talking, found out they could buy these GPS jammers off the internet. They put them in their trucks, and they never really thought about the impact of what they were doing. But they get to the truck stop, turn on the jammer, drive home, park the truck over the weekend, and leave the jammers on. Drive back to the truck stop, turn it off. And as far as the company is concerned, they never left the truck stop. That's not the true state. And every GPS antenna they passed on the way to their home, of course, ended up getting jammed. some of the other organizations, cab drivers, package delivery type folks who also didn't want to be tracked. These are the biggest impact points that we have seen in the industry today. Now, the last one on the list is the environmental impacts that we actually see, which is, as an example, an HVAC compressor all of a sudden went bad on the roof. It just so happened the GPS antenna was mounted to the HVAC unit, which is improper installation. And the HVAC compressor was generating a harmonic, which was actually interfering with our GPS, creating a noise burst. As Mark pointed out also, antenna fields. When we put the GPS antenna up 6 years ago up on the roof, it was a clear roof. 6 years later, all of a sudden we have 17 antennas encircling our GPS receiver there. So that's the kind of situations you can run into. In the last one, new building construction. You would think if somebody is tearing down a 4-story building and all of a sudden putting up a 20-story building, all of a sudden we see impact, we see block signal. However, a worst case condition actually is not new building construction, but new units being added to the existing building infrastructure, rooftops. They put new penthouses up there. They take and put, as an example, they built a new air conditioning system and they put a big aluminum shield to make it not seeable from the street side. It acts as a natural block to our antenna systems. Now, when we talk about to the carrier industry, what is the cost of impacts to business? Well, when we lose GPS at a central office, our sync clock, we see a loss of SS7 links, which immediately shuts down all E911 or 911 processing services. Major impact. That means no fire, no ambulatory, no police can be contacted by the local market. Loss of long distance, direct correlation to loss of revenue to the carrier. Now, some of the not so subtle type impacts. In the industry, we've always said Ethernet, our data services aren't impacted by synchronization. Well, that was true until we began to deploy 100 gigabit Ethernet links. Most manufacturers today actually have PTP v2 or 15A v2 type standards synchronization built into these cards. The reason why is for the phasing. It is a buffer control mechanism. It allows for the efficiency of data packets to go through the Ethernet network without any delay, reducing the latency of data throughput on those 100 gigabit card ports. Now, a more direct impact of loss of sync is SONET and SDH carriers. Again, we've always had a situation where 20 years ago, we put Ethernet across SONET or across SDH networks. Today, we're putting SONET and SDH services across the Ethernet using pseudo-wire. So when we lose synchronization across these networks or in a CO, we begin to give data hits into that throughput, which causes both, you know, if it's a DS3 pseudo-wire, we're seeing heavy hits or dropouts on the DS1 level. The next service layer is VoIP. In the VoIP world, we've used bit timing to provide VoIP with synchronization. We've also used GR303, which is also another T1 type form of synchronization. And when we lose sync in an office, frequency sync in an office, it directly affects and causes voice dropouts across the network. Again, it's an impact to quality. The last item, D on the list, is quality of service impact to the wireless providers. As a carrier, we provide a lot of backhaul for a lot of the wireless carriers. When we see a loss of sync in the network, with the 4G LTE networks especially, and the 3G network's not as critical there, but we do see some impact. As we move forward in the industry with 5G technology, actually 5G radio, because of its increased bandwidth loads, we're actually going to see more impact to the network. So sync diversity architectures to be able to prevent these impacts. Network diversity using PDP-v2, we use redundant sync cards, 2E, 3E in our clocks, in our grandmasters, in order to try to get around a lot of these kind of impact situations. With the 1588v2 as a secondary sync source throughout our network, if we lose GPS, we can pick up both TOD and phase off of that 1588v2 source to feed that central office with synchronization. In the redundant clock card infrastructure, as well as with redundant GPS antennas on the roof, 20 years ago, 15 years ago, it was a very standard practice to put 2 GPS antennas on the roof and feed to a single grandmaster. Well, in today's architecture, because we're actually using both GPS and PDP-v2 infrastructure as a secondary source, if I can get this to switch. Got another one in here somewhere. There we go. As you can see, what we're doing from a network topology standpoint, we have grandmasters in a CO, but we've also added a PTP boundary clock functionality. So we have one GPS going to the grandmaster, another GPS going into the PTP boundary clock, and we have then a primary and secondary NTP sync source in every CO. The way that we're using PDP-v2 as a secondary source is over our 100 gigabit link between CO to CO. We're also now doing synchronization as a service, pushing both bits down to the network, sync E to the network over Ethernet, and PTP-v2 or 58v2 over the Ethernet network to our network elements. However, we're also pushing the synchronization 1588v2 all the way down actually to the tower for wireless and actually all the way down into our customer access networks today. I'd like to thank you from Windstream and from ATIS to allow us to bring this information to you. At this time, I would like to introduce our next speaker, Richard Thunderberg. He's Timing Systems Architect with Trimble. Thank you, Richard.
Thank you, Richard, for the introduction. Yes, as introduced, I am the Timing System Architect at Trimble, where we manufacture the GPS receivers. Specifically, the timing type receivers is what we're going to be focusing on here. So the market perception, GPS has been making it into the system, into the news quite a bit. These are kind of dated articles, but you can see there's headlines here of GPS flaw, lit terrorist attack, GPS spoofing is new game. Even back when Malaysia flight was lost, they were wondering about the fact that maybe GPS was blocking and caused that plane to go down. So that's why we're doing this presentation, is what is going on here with GPS. So let's go ahead and take a look at some of these information about GPS and GNSS. As Mark mentioned, the GNSS, the more generic term. Since the launch of the first CDMA networks, there's over 685 commercial networks in over 120 countries that rely on GPS for timing. Out of the 15 critical infrastructures, timing is used in 15 of those. According to the U.S. study, out of 20 different methods of getting time, all but 2 of them were ultimately dependent on GPS. The reason for that being is by the very nature of the name, GPS being global, allows us to transfer time across very large areas and have that time be quite accurate. Currently no other method is capable of doing that, and that's what other studies are looking at right now. The key thing is 1588 or PTP v2 is also used, but ultimately PTP also relies on GPS. So when we're talking about these vulnerabilities, ultimately it's also in the PTP, because then since PTP is getting its time ultimately from GPS, GNSS, it has the same type of issues that can happen within a standard GPS installation. Talk a little bit about jamming versus spoofing. One of the things with jamming is that it's generally unintentional. These are the things that Richard mentioned and Mark, with antenna placement, with the Richard's example of the AC unit going into some kind of a oscillation that caused the signal to be jammed. Even the jammers that the truck drivers use, that would be an intentional jamming, but it's just a frequency that's being transmitted at a stronger level than the GNSS signal. As Mark mentioned, the GNSS signal is very, very low signal. It does not take much to actually block that out. Jamming is also very easy to produce. But the key thing with jamming is it's generally a limited area. Unless you have a fairly high-powered transmitter, you're not going to be able to block out huge portions, city, state type things. It's usually a general localized. And if it is a strong jammer, easier to find. There's techniques to locate where that jamming is coming from. Spoofing. Mark's introduction of spoofing was very good, showing where you have this signal that's overlaying GPS and can draw that signal away. The key thing with spoofing, it is always intentional. There is not any currently known system that can accidentally spoof GPS. So if spoofing is occurring, it's an intentional counterattack or against the GPS signal itself. It requires the full GNSS data reproduction. You can alter the time position information. It's complex. It's not a simple system to set up, but more and more of these GPS or GNSS simulators are becoming available. And so again, it is possible, and it is a limited area. And the real problem here is that the spoofing is very difficult to distinguish from the real signal. But again, it requires much more knowledge than your average off-the-street user is going to do. So if spoofing is occurring, it's a sophisticated attack of someone trying to mess with the system. Thus far, Trimble has never seen a spoofing attack in the real world. We've only seen spoofing in a lab environment. Since jamming is the predominant mechanism that's causing the issues with GPS at this point, where the signal is actually just blocked out completely. Some of the key things here is, remember, we're talking timing receivers for this webinar. We're not talking GPS in your car. We're not talking your GPS as you're out for your run, your morning jog. We're talking a timing receiver that's been installed into an environment. So the key is to know the environment, as Richard had mentioned. Placement of that antenna. You need to validate, where was that antenna put? Is it a good location? Does it have a good view of the sky, or is that signal going to be blocked from the get-go? Also, are there already known sources of GPS jamming type environments? GPS is at up in the 1.5 gigahertz range, so you want to make sure you don't have those kind of signals within your system. What kind of antenna are you deploying? You want to have an antenna that already has built in some of these multi-layers of filtering, larger ground planes. You want high linearity in the linear amplifier within that antenna. we'll talk a little bit more about all of these in the next few slides. But the key that has generally been seen in real installations is this antenna installation. Where is that antenna located? What's going on? We've even had instances where, this is an odd one, cows out. So we had an antenna installed out in the field, and every day at a certain time, the GPS signal would be lost. And we finally had to send out a technician to see what was going on. And at the same time of the day, the farmer would feed the cattle. The cows would come out. The antenna was mounted too low. The cows thought the antenna was a salt lick. They would then have their heads over the antenna blocking the GPS signal. We raised the antenna a couple of feet, get it out of the way of the cows. The problem went away. So just the antenna installation is really a key issue within the use of GPS. The bandpass information. Shown here, you can see those straight vertical lines. That's essentially the range of what you want to see for the GPS signal to carry all the GPS signaling. The blue line represents what may be just a general antenna. And you can see that that antenna would accept a lot of interfering noise from well outside the range of the antenna. And again, GPS is very low signal. So if you can get that signal much, much higher than what the gain of the receiver is able to do, you've blocked GPS. So you can see the red line is an antenna with a multi-level filtering, getting a much tighter filtering effect for that antenna signal to pull those skirts in of that, to block additional information that may be coming in from well outside the signaling area that you're interested in. The modern receivers of today can handle in-band jamming in the 50 and 60 dB range. So filtering is a key issue. Elevation pattern. So your antenna, when antennas are built, they're built to focus on the sky. That's what you're looking at. Unless you have a omnidirectional antenna, which might be used, say, in aircraft that may be flipping upside down or doing something along those lines. But for timing receivers, again, those antennas are generally going to have focusing upward. So what you do is you put a ground plane underneath that antenna. Now what happens is signals below that horizon of that ground plane are naturally blocked. And since these are timing receivers, those antennas are usually mounted high. They're high up. So anything on the ground level is not going to be in effect. And so if those blocked with that ground plane, then you have a much better chance of keeping those bad signals out to start with, which is the key thing with jamming. If you can keep those spurrent frequencies out of the antenna, out of that front end of that GPS, you've essentially eliminated the jamming causes. Some other mitigation techniques, and I think Sarah is going to be looking at some of these. The secondary reference signal. No matter what, in any timing system, if you have a single point of time, you have a single point of failure within that timing system. So you want a secondary reference signal. Some of the cases are you could have dual GNSS band. You could have GPS with L1 and L2. You could have multi-constellation. The U.S. is not the only positioning system out there anymore. That's where the GNSS comes from. There's now satellite systems set up in Russia, in China. The European one for Galileo has gone fully active now. So there's multiple constellations that can be utilized. And as an example, one of the things that made the news recently, within the last year or so, was when GPS had a 13 microsecond error in UTC time. None of the receivers that had available another constellation to look at, GLONASS, they do, Galileo, None of those systems exhibited the UTC offset of 13 microseconds because the receiver tossed the signals from GPS saying those are incorrect because it's moved more than what this other system is saying it moved, and it tossed those signals. So those receivers continue to generate proper time. Within a timing receiver, if you are using it for precision timing and clocking, you're also going to have a good quality oscillator in there. Those oscillators also give you a reference. If suddenly GPS is telling you that your time has jumped, let's say, to 13 microseconds, you know the oscillator could not have jumped 13 microseconds. You already have a voting scheme. You can say GPS is incorrect and either go to a holdover situation where you rely on the quality of that oscillator, or you just raise flags and say time is not valid, select something else to use. And as Richard had mentioned, PTP or SYNC-E as a secondary reference is also very useful because that's at a dispersed location. So even though PTP is ultimately derived from GPS, if you're experiencing a jamming or a spoofing condition within your site, remember I had started this by saying those are localized issues. So if you're experiencing that and you have PTP that you're getting from a geographically separate site, chances are very good that is not being jammed or spoofed. Now you have something else to compare time against and disqualify that GPS signal. Improved sensitivity, multi-stage filtering, the weak signal extraction, and proper antenna site selections are all other very useful mitigation techniques if you think you are experiencing jamming or, like I said, spoofing, which we've never really seen in the wild yet for timing receivers. All of these mitigation techniques can be used to aid in that, getting rid of those signaling problems. So kind of wrap up my section here. So GNSS is still the only solution for distributed time. 1588 is being used to distribute that time, but it ultimately is based on GPS or GNSS. So doing a wide area distribution of time, currently GPS is the only solution that is operational. Multi-constellation, multi-band provides the most robust solution for a single receiver installation. There's also different mitigation techniques that are being done within the receivers themselves to aid for some of these. Then the application and the in-use case, that will determine the selection of the timing source. So you may be able to use something that's not as accurate, say, as GPS for your timing. If you only need a millisecond, you can use other techniques to get the time. But if you need sub-millisecond into the microsecond and sub-microsecond range, you're going to pretty much need to use GPS, and you'll want something else to back that up, to be able to compare against, to be able to give you a stable reference to make sure that something else is not happening with GPS. And at this point, I'd like to turn it over to Sarah out of the Homeland Security.
Great. Thank you so much, Richard. I think we've already had a lot of great tips and information today. And so what I would like to do is kind of give you the national perspective of some of the things that we're working on in support of this issue. We've already talked a lot about the threat space, so to speak, with the jamming and spoofing. We kind of think of it as jamming is essentially a denial of service, and where spoofing is kind of like a deception attack. And so the potential impacts associated with spoofing are quite concerning, given that, much of our critical infrastructure, as was pointed out earlier, relies on GPS for that synchronized timing signal. One thing I will mention, a couple months ago, there were a number of reports of spoofing incidences in Russia outside the Kremlin. So folks that were driving by the Kremlin, their GPS was actually telling them that they were out by the airport. That, and then, I think this threat space is continuing to increase, and you never know what you're going to get. So, for example, the Pokemon Go craze was, a lot of folks were then trying to deceive their phones into thinking that they were somewhere else, so that they could collect more Pokemons. And another aspect of that is that this information is becoming more public at recent hacker conferences and blog posts and stuff like that. So the information and the know-how and the availability of the equipment is all much more prevalent than it has been in the past, and so that's one of our driving concerns as well. Another concern is that we do understand that we have a reliance on GPS, but we don't always understand exactly what the cascading impacts could really be if we were to lose, whether it's synchronization in a communication network or what the cascading impacts down from that are. And so those are some of the things that we are looking at over here at DHS. And so to address this and kind of to put it all into one picture, we've kind of come up with this risk management and program strategy that really kind of breaks things down into different layers. And so the objective is to get at this from different layers here, but have a holistic approach and view, and so that, together, when all this comes together, we are much more resilient. And so starting at the bottom here, we call mitigation via vulnerability assessment and impact assessment. So this is really, all the way down at the device level. How are these GPS receivers behaving? And so we're testing them in the lab in open air settings, and hopefully we'll get to a point where we can do some system level testing to have a really good understanding of what the actual vulnerabilities are, to validate those vulnerabilities and inform us in the mitigations about what to do. So I think what, in a lot of senses, many of these receivers are kind of designed to be very trusting, more like a radio than a computer in the environment that we have to be considerate of today. And so we are working with manufacturers and others to try and increase the awareness of the vulnerabilities here, and also, start to build in some software assurance and those types of things into the next sort of version of these receivers that comes out. Like it sets up into the next layer where it's kind of mitigation versus awareness. So we've issued a number of best practices, and I'll show you a few of them today, that hit on a lot of things that were already talked about. We spent a lot of time talking about antenna placement, all of that stuff. So we've got best practices out there that will hopefully help guide folks in some of the things that they can do to kind of reduce their potential vulnerability. The next layer up from that is what I call mitigation via improved equipment. So this is taking it even further, looking at specialized antennas and more robust receivers. What alert and monitoring systems do we need, if any, to just provide better situational awareness when something is going on. And then finally, the last point, which was hit on by Richard's presentation as well, is, in order to truly be resilient, we have to diversify. So what other timing sources can we look at that can provide the needs, particularly for critical infrastructure timing? And so I'll hit on a few of these and examples of what we're doing in each of them. So going on to the vulnerability assessment and awareness, we are hosting a number of test events, and the idea here is to really validate what we've been testing in the lab in live sky environments, and then also provide this as an opportunity for industry stakeholders, whether it's manufacturers or owners and operators, to come see what the potential impacts are. We had a big exercise last year, 2016, at White Sands Missile Range that was primarily geared at the first responder community, so for them to understand what the impacts are to them and their ability to, conduct their mission if GPS and we also started to look at comms, is jammed or spoofed. How are they going to work around it? And then what type of resilience do they need in their equipment. We had another event in October at Savannah River National Laboratory, and I'll get to that one at the end. But we also have some future events planned. The next one just coming up here in April, where it's really focused on equipment manufacturers to allow them to come and test their equipment in a live sky environment that we create, so that they can understand, you know, what are some of the areas that they may want to work on for improving their resilience. And then again, we will be having more jamming exercises as well. So we are planning kind of a series of events in this nature to help push us along the path to greater awareness of the issues and increased resiliency to them. Moving on to some of our best practices. This is the latest one that we issued just this past January, entitled Improving the Operation and Development of Position Navigation and Timing Equipment Used by Critical Infrastructure. In this set of best practices, we've really broken it up into kind of different stakeholders. So there's end user guidance, something that, you know, from our perspective, we'd be having the critical infrastructure owners and operators. This is kind of the section for them to understand what it is that they can do now to decrease their vulnerability and things that they ought to be looking for in the future. And then there's another section that really focuses on the manufacturer. So what are some capabilities that they may want to consider putting into their equipment now to kind of help increase their resilience. We had another set of best practices, and these are available online. The links are here on the screen for you. Another set of best practices that was much more focused on fixed timing receivers and fixed locations. This was issued, I guess, 2 years ago now, but really focused a lot on the receiver the antenna positioning, hiding your antenna from view, making sure that you've got the clean air space, and some of the things that our other presenters already hit on. So hopefully you'll find that these are pretty good resources, and we look to publish more best practices as we can. Moving on to potential mitigating equipment. This is just one example of the types of things that we're working on. So similar to what Richard talked about, this is a horizon ring nulling timing antenna. So the idea, again, is that, you know, any true GPS signal should be coming from the sky, and so, you know, we want to limit the antenna's entry points from below the horizon here. And so what we've done in this particular case, we've worked with MITRE to develop a very low-cost horizon ring nulling antenna that we're looking to make available via no-cost licensing agreement to different manufacturers who may be interested in commercializing this. So again, just one example of the types of mitigation efforts that we're working on. Then finally, the last piece, and maybe one of the most important pieces, is the need for diversity in our source of timing. So we have a pretty large effort, and this is really across the federal space, other agencies working this with us, but to first understand what are our actual requirements for PNT across the different critical infrastructure sectors, so that we can then start to evaluate and determine what needs to be done to perhaps create you know, a complementary capability or a backup capability to GPS, so that, you know, we don't have a single source that we're all relying on. So right now we've gone and done a deep dive within the electricity subsector and the wireless sector, and we're looking at a couple more sectors to just make sure first that we fully understand what the requirements are for PNT, and then start looking at, you know, potential technologies that are available to meet those, and then if there are no technologies available to meet those requirements, you know, what research and development opportunities do we need to look towards investing in. So while we are doing the requirements, we are also exploring different technologies, and you've probably heard about a couple of these already. For example, ELRAN. We had a demonstration last April at the New York Stock Exchange using the ELRAN signal, and we were able to receive it within the Stock Exchange building to within 30 nanoseconds of a UTC reference, where we were not able to get GPS signals. So that's, one potential possibility for technology. We're also looking at the capability of Iridium to deliver a timing signal, and so this is the testing that we conducted at Savannah River National Lab, where the Iridium signal was able to be received to within 200 nanoseconds of GPS, even when we were jamming the GPS signal and we weren't able to receive that. So two examples. We are continuing to work in this space even more, but I think that gives you an overview of our approach to this problem, and hopefully from the other presenters as well, you've seen the need for us to be engaged here and understand what the threats and vulnerabilities are. And I do think that the threat space continues to increase, and so we want to make sure that we're doing what we can to make sure that we're resilient enough to face those potential threats. And with that, I will turn it back over to Mark.
Thanks, Sarah. At this time, we'll begin the Q&A portion of the webinar. Thank you for those who've submitted questions online. I have a first question that I'm going to address to Richard Funderburk. I'd like your thoughts on the reliability of the GPS source, the satellites, the ground, the ability of the antenna to block jamming. How reliable can GPS be?
Thank you, Mark. The GPS source itself is highly reliable. When you consider that GPS has been deployed since the 80s, and we can probably count on one hand, as in maybe once or twice, that anything has happened from the ground stations. So GPS as itself is highly reliable because it's controlled by the DoD and all, and they see it as highly reliable system that they need 100% of the time also. So from that aspect, GPS is very reliable. From the aspect of something happening to the signal being transmitted, it's also very reliable. When we've seen in this presentation various issues of occurrences of GPS. So when you consider the millions of hours that GPS is in use every year, and then you're looking at outages of an hour, 2 hours, unless it's an installation problem, GPS tends to be highly reliable.
Great, thank you, Richard. The next question I'm going to address to Sarah. The question is, what are the two methods of perhaps 20 for getting time that were not dependent on GPS? And how does a non-US GNSS signal for a secondary time, how does a user access that when there is an FCC prohibition on using non-GNS signals?
So I'll take that second question first because it is a true statement, a little bit of a gotcha. So those signals are not authorized by the FCC, have not been licensed within the United States. The fact is that they are still in the air. So I think any decision to rely on those may be, maybe have some risk associated with it, just given kind of the current state of the policy. As for the two methods out of 20 for getting time that were not dependent on GPS, I think that was in Richard's presentation, so he may have the better reference for that.
Yes, this is Richard. Yeah, those other two were probably going to be tied into NTP, coming specifically from NIST, where that system does not rely on GPS. It relies on the timing from NIST and all to be able to derive and come up with that software clock that's running those NTP servers. So those were non-precise types of timing distributions. So in the order of maybe just within a second or less than a second down to maybe 100 milliseconds.
Okay, thank you. I have another question that's been submitted, and this one's for Richard Lindsey. With GMs being deployed away from towers, how many hops is that away? And are BCs, boundary clocks, used to improve the performance of the slave? Is the slave at the tower or the last hop before the tower, and which profile is used?
Yes, sir. So in the architecture of deploying PTP across the network, we always do try to limit the hops to 4 hops. However, the more important qualifier actually is based on PDV measurements as well as latency of the Ethernet transport to the tower. And yes, the slave is normally always at the tower. We do have some cases where it's actually at the last point prior to the tower, but in most cases, architecturally, we do try to put the slave at the tower itself. Now, the profile that's used is the telecom profile, and it really depends on which of the two that we want to deploy and based on what the timing requirements are for that particular tower. If they're running a 4G LTE type platform or a 5G type platform out of that tower.
Thank you, Richard. I have another question for Richard Funderburk. With potential jamming sources, you talked about the layered filtering. How well can that prevent jamming? I know you talked about 50 to 60 dB. What does that mean in the real world in terms of, you know, a jammer out there? How far away? How strong? What kind of jammers can that block?
Well, with the, you know, I'm no RF level expert, but 50 to 60 dB, the GPS signal is down around minus 130 dBm. So when you're looking at a 50 or 60 dB signal above the ground plane, you're looking at a pretty strong signal that you would need to be almost right on top of the antenna to be able to inject that through the air. Otherwise, you're going to need several watts, maybe even up into the hundreds of kilowatts to be able to get that from any real distance from the antenna.
Well, thank you. I think that concludes the questions. I'd like to bring the webinar to a close. First by talking about some options for learning more about synchronization and GPS and GNSS vulnerability. There will be a workshop on synchronization and timing systems in San Jose coming up. That's April 3rd through 6th. And you can find more about that by going to atis.org/WSTS. I'd like to thank everyone for joining us today. And on behalf of ATIS, thank you again for attending today's webinar. All registered attendees will receive a follow-up email containing links to a recording of this, as well as the slides from the presentation. And thank you for joining, and enjoy the rest of your day.